Robust statistics are statistics with good performance for data drawn from a wide range of probability distributions, especially for distributions that are not normal. Robust statistical methods have been developed for many common problems, such as estimating location, scale, and regression parameters. One motivation is to produce statistical methods that are not unduly affected by outliers. Another motivation is to provide methods with good performance when there are small departures from parametric distributions. For example, robust methods work well for mixtures of two normal distributions with different standard deviations. Under this model, non-robust methods like AT-tests work badly. Introduction. Robust statistics seeks to provide methods that emulate popular statistical methods, but which are not unduly affected by outliers or other small departures from model assumptions. In statistics, classical estimation methods rely heavily on assumptions which are often not met in practice. In particular, it is often assumed that the data errors are normally distributed, at least approximately, or that the central limit theorem can be relied on to produce normally distributed estimates. Unfortunately, when there are outliers in the data, classical estimators often have very poor performance. When judged using the breakdown point and the influence function, described below, the practical effect of problems seen in the influence function can be studied empirically by examining the sampling distribution of proposed estimators under a mixture model, where one mixes in a small amount of contamination. For instance, one may use a mixture of 95% a normal distribution, and 5% a normal distribution with the same mean but significantly higher standard deviation. Robust parametric statistics can proceed in two ways: by designing estimators so that a pre-selected behavior of the influence function is achieved, by replacing estimators that are optimal under the assumption of a normal distribution with estimators that are optimal for, or at least derived for, other distributions. For example, using the t-distribution with low degrees of freedom or with a mixture of two or more distributions. Robust estimates have been studied for the following problems: estimating location parameters, estimating scale parameters, estimating regression coefficients, estimation of model states in models expressed in state space form, for which the standard method is equivalent to a Kalman filter. Examples: the median is a robust measure of central tendency, while the mean is not. The median has a breakdown point of 50%, while the mean has a breakdown point of 0%. Trimmed estimators and winsorized estimators are general methods to make statistics more robust. L-estimators are a general class of simple statistics, often robust, while M-estimators are a general class of robust statistics, and are now the preferred solution, though they can be quite involved to calculate. Definition. There are various definitions of a robust statistic. Strictly speaking, a robust statistic is resistant to errors in the results produced by deviations from assumptions. This means that if the assumptions are only approximately met, the robust estimator will still have a reasonable efficiency and reasonably small bias, as well as being asymptotically unbiased, meaning having a bias tending towards zero as the sample size tends towards infinity. One of the most important cases is distributional robustness. Classical statistical procedures are typically sensitive to long-tailedness. Thus, in the context of robust statistics, distributionally robust and outlier-resistant are effectively synonymous. For one perspective on research in robust statistics up to 2000, see Portnoy and E. A related topic is that of resistant statistics, which are resistant to the effect of extreme scores. Example: speed of light data. Gelman et al. In Bayesian data analysis, consider a dataset relating to speed of light measurements made by Simon Newcomb. The datasets for that book can be found via the Classic Datasets page, and the book's website contains more information on the data. Although the bulk of the data look to be more or less normally distributed, there are two obvious outliers. These outliers have a large effect on the mean, dragging it towards them, and away from the center of the bulk of the data. Thus, if the mean is intended as a measure of the location of the center of the data, it is, in a sense, biased when outliers are present. Also, the distribution of the mean is known to be asymptotically normal due to the central limit theorem. However, outliers can make the distribution of the mean non-normal even for fairly large datasets. Besides this non-normality, the mean is also inefficient in the presence of outliers unless variable measures of location are available. Estimation of location. The plot below shows a density plot of the speed of light data, together with a rug plot. Also shown is a normal QQ plot. The outliers are clearly visible in these plots. Panels and of the plot show the Bootstrap distribution of the mean and the 10% trimmed mean. The trimmed mean is a simple robust estimator of location that deletes a certain percentage of observations from each end of the data, then computes the mean in the usual way. The analysis was performed in R and 10,000 Bootstrap samples were used for each of the raw and trimmed means. The distribution of the mean is clearly much wider than that of the 10% trimmed mean. Also note that whereas the distribution of the trimmed mean appears to be close to normal, the distribution of the raw mean is quite skewed to the left. So, in this sample of 66 observations, only 2 outliers cause the central limit theorem to be inapplicable. Robust statistical methods, of which the trimmed mean is a simple example, seek to outperform classical statistical methods in the presence of outliers, or, more generally, when underlying parametric assumptions are not quite correct. Whilst the trimmed mean performs well relative to the mean in this example, better robust estimates are available. In fact, the mean, median and trimmed mean are all special cases of estimators. Details appear in the sections below. Estimation of scale. The outliers in the speed of light data have more than just an adverse effect on the mean. The usual estimate of scale is the standard deviation, and this quantity is even more badly affected by outliers because the squares of the deviations from the mean go into the calculation, so the outliers' effects are exacerbated. The plots below show the Bootstrap distributions of the standard deviation, median absolute deviation and QN estimator of scale. The plots are based on 10,000 Bootstrap samples for each estimator, with some Gaussian noise added to the resampled data. Panel shows the distribution of the standard deviation, of the MAD and of QN. The distribution of standard deviation is erratic and wide, a result of the outliers. The MAD is better behaved, and QN is a little bit more efficient than MAD. This simple example demonstrates that when outliers are present, the standard deviation cannot be recommended as an estimate of scale. Manual screening for outliers. Traditionally, statisticians would manually screen data for outliers, and remove them, usually checking the source of the data to see if the outliers were erroneously recorded. Indeed, in the speed of light example above, it is easy to see and remove the 2 outliers prior to proceeding with any further analysis. However, in modern times, datasets often consist of large numbers of variables being measured on large numbers of experimental units. Therefore, manual screening for outliers is often impractical. Outliers can often interact in such a way that they mask each other. As a simple example, consider a small univariate data set containing one modest and one large outlier. The estimated standard deviation will be grossly inflated by the large outlier. The result is that the modest outlier looks relatively normal. As soon as the large outlier is removed, the estimated standard deviation shrinks, and the modest outlier now looks unusual. This problem of masking gets worse as the complexity of the data increases. For example, in regression problems, diagnostic plots are used to identify outliers. However, it is common that once a few outliers have been removed, others become visible. The problem is even worse in higher dimensions. Robust methods provide automatic ways of detecting, downweighting, and flagging outliers, largely removing the need for manual screening. care must be taken. Initial data showing the ozone hole first appearing over Antarctica were rejected as outliers by non-human screening variety of applications. Although this article deals with general principles for univariate statistical methods, robust methods also exist for regression problems, generalized linear models, and parameter estimation of various distributions. Measures of robustness. The basic tools used to describe and measure robustness are the breakdown point, the influence function, and the sensitivity curve. Breakdown point. Intuitively, the breakdown point of an estimator is the proportion of incorrect observations an estimator can handle before giving an incorrect result. For example, given independent random variables and the corresponding realizations we can use to estimate the mean. Such an estimator has a breakdown point of 0 because we can make arbitrarily large just by changing any of. The higher the breakdown point of an estimator, the more robust it is. Intuitively, we can understand that a breakdown point cannot exceed 50% because if more than half of the observations are contaminated, it is not possible to distinguish between the underlying distribution and the contaminating distribution. Therefore, the maximum breakdown point is 0.5, and there are estimators which achieve such a breakdown point. For example, the median has a breakdown point of 0.5. The X% trimmed mean has breakdown point of X% for the chosen level of X. Huber and Mirona al. contain more details. The level and the power breakdown points of tests are investigated in He al. Statistics with high breakdown points are sometimes called resistant statistics. Example: speed of light data. In the speed of light example, removing the two lowest observations causes the mean to change from 26.2 to 27.75, a change of 1.55. The estimative scale produced by the QN method is 6.3. We can divide this by the square root of the sample size to get a robust standard error, and we find this quantity to be 0.78. Thus, the change in the mean resulting from removing two outliers is approximately twice the robust standard error. The 10% trimmed mean for the speed of light data is 27.43. Removing the two lowest observations and recomputing gives 27.67. Clearly, the trimmed mean is less affected by the outliers and has a higher breakdown point. Notice that if we replace the lowest observation, -44, by -1000, the mean becomes 11.73, whereas the 10% trimmed mean is still 27.43. In many areas of applied statistics, it is common for data to be log transformed to make them near symmetrical. Very small values become large negative when log transformed, and zeros become negatively infinite. Therefore, this example is of practical interest. Empirical influence function. The empirical influence function is a measure of the dependence of the estimator on the value of one of the points in the sample. It is a model-free measure in the sense that it simply relies on calculating the estimator again with a different sample. On the right is two keys by weight function, which, as we will later see, is an example of what a good empirical influence function should look like. In mathematical terms, an influence function is defined as a vector in the space of the estimator, which is in turn defined for a sample which is a subset of the population, is a probability space, is a measure space, is a parameter space of dimension, is a measure space. For example, is any probability space. The definition of an empirical influence function is: let an I, D, and is a sample from these variables, is an estimator. Let the empirical influence function at observation is defined by. Note that what this actually means is that we are replacing the ith value in the sample by an arbitrary value and looking at the output of the estimator. Alternatively, the EIF is defined as the effect on the estimator of adding the point to the sample, influence function and sensitivity curve. Instead of relying solely on the data, we could use the distribution of the random variables. The approach is quite different from that of the previous paragraph. What we are now trying to do is to see what happens to an estimator when we change the distribution of the data slightly. It assumes a distribution, and measures sensitivity to change in this distribution. By contrast, the empirical influence assumes a sample set, and measures sensitivity to change in the samples. Let be a convex subset of the set of all finite-signed measures on. We want to estimate the parameter of a distribution in. Let the functional be the asymptotic value of some estimator sequence. We will suppose that this functional is Fisher consistent, i.e., this means that at the model, the estimator sequence asymptotically measures the correct quantity. Let be some distribution in. What happens when the data doesn't follow the model exactly but another, slightly different, going towards? We're looking at which is the one-sided directional derivative of it, in the direction of. Let is the probability measure which gives mass 1 to. We choose. The influence function is then defined by. It describes the effect of an infinitesimal contamination at the point on the estimate we are seeking, standardized by the mass of the contamination. For a robust estimator, we want a bounded influence function, that is, one which does not go to infinity as x becomes arbitrarily large. Desirable properties of an influence function which bestow it with desirable performance are finite rejection point, small gross error sensitivity, small local shift sensitivity, rejection point, gross error sensitivity, local shift sensitivity. This value, which looks a lot like a Lipschitz constant, represents the effect of shifting an observation slightly from to a neighboring point, i.e., add an observation at and remove one at. Estimators. Historically, several approaches to robust estimation were proposed, including R-estimators and L-estimators. However, M-estimators now appear to dominate the field as a result of their generality, high breakdown point, and their efficiency. See Huber. M-estimators are a generalization of maximum likelihood estimators. What we try to do with MLEs is to maximize or, equivalently, minimize. In 1964, Huber proposed to generalize this to the minimization of where is some function. MLE are therefore a special case of M-estimators. Minimizing can often be done by differentiating and solving, where several choices of and have been proposed. The two figures below show four functions and their corresponding functions. For squared errors, increases at an accelerating rate, whilst for absolute errors, it increases at a constant rate. When Winsorizing is used, a mixture of these two effects is introduced. For small values of x, increases at the squared rate, but once the chosen threshold is reached, the rate of increase becomes constant. This Winsorized estimator is also known as the Huber loss function. 2 keys by weight function behaves in a similar way to the squared error function at first, but for larger errors, the function tapers off. Properties of M-estimators. Notice that M-estimators do not necessarily relate to a probability density function. Therefore, off-the-shelf approaches to inference that arise from likelihood theory cannot, in general, be used. It can be shown that M-estimators are asymptotically normally distributed, so that as long as their standard errors can be computed, an approximate approach to inference is available. Since M-estimators are normal only asymptotically, for small sample sizes it might be appropriate to use an alternative approach to inference, such as the Bootstrap. However, M-estimates are not necessarily unique. Also, it is possible that any particular Bootstrap sample can contain more outliers than the estimator's breakdown point. Therefore, some care is needed when designing Bootstrap schemes. Of course, as we saw with the speed of light example, the mean is only normally distributed asymptotically, and when outliers are present, the approximation can be very poor even for quite large samples. However, classical statistical tests, including those based on the mean, are typically bounded above by the nominal size of the test. The same is not true of M-estimators, and the type 1 error rate can be substantially above the nominal level. These considerations do not invalidate M-estimation in any way. They merely make clear that some care is needed in their use, as is true of any other method of estimation. Influence function of an M-estimator. It can be shown that the influence function of an M-estimator is proportional to page 45, which means we can derive the properties of such an estimator when we know its function, with the given by choice of psi and rho. In many practical situations, the choice of the function is not critical to gaining a good robust estimate, and many choices will give similar results that offer great improvements, in terms of efficiency and bias, over classical estimates in the presence of outliers. Theoretically, functions are to be preferred, and Tukey's by-weight function is a popular choice. Moron al. recommend the by-weight function with efficiency at the normal set to 85%.